Okay, so that took 5 minutes, but if it can stretch, it's good. No, it's fine. Okay, I mean, this is pretty informal, so thank you so much for coming to this meeting. I think, do you want to say something? This is like the second event, or is this the only event in this?
No, we had a couple of office
events.
visits and
Yeah.
other sessions, but I think it's information session is the first one for this semester.
Yeah. So, okay, so what I thought I'll do is I gave us the same talk, slightly different, but same talk at Masters in Management Analytics. It's very similar to MSPA program that we have here at Queen's University in Canada. So I'm gonna kind of reuse the same material. So I don't know, initially we had a slightly different objective, but this objective today is to just introduce you to some research, applied machine learning research that's happening in the department. And so since I'm in the department, I'm going to mostly talk about my work, but just give you a flavor of what types of research work. It's not too different from what you generally see in your courses since you're already at master's level, but it's a little bit, maybe you'll see that it's a natural path if you continue to pursue this. It's just about adding more creativity to your ML tools that you already are getting aware of. Okay. So yeah, if you have questions anytime, you can just pause me. Okay, so since I don't know some of you people, so I have some experience, not as much as some of you guys, but like some experience in the industry. So before I started here, I was at a research lab, and so where the focus was on just patenting new, I guess, invention disclosures or innovations. And then I started here. It's been more than half a decade. So as part of this, I do consult with some organizations, external organizations. And also before that, I had, very similar to you guys, I did some internships at Apple and other places. So you can obviously add me on LinkedIn and stuff. I think I know some of you are already on LinkedIn, but add it with me. Okay, so what's the goal for this talk? Okay, it's a talk which is basically introducing research. So I'm not going to get into any particular research thread in detail. That's not the goal. Basically, the objective is to showcase some more applications that you might have seen in some courses, might not have, and see what research projects look like compared to master's projects, and give you a sense of this is the, given that AI is now even more mainstream than it was last decade. Last decade, there was a lot of innovation because of neural networks and GPUs. This decade, a lot of innovation driven by large language models and vision models and so on. So there's going to be a lot of use of these tools and new ways to connect the tools to the actual business application. So today, there's still gaps, and that's why there are so many new companies coming out to kind of bridge that gap. So maybe some of us can fill those gaps in business. So there are 4 applications that I've chosen, but are 4 projects, you can say. But I will just focus on as many as needed. We don't have to cover all 4. We'll just look at 2 or 3, depending on how much we cover. So the first one is called crowd shipping. I think I already pitched this in my deep learning class, maybe, but it was very quick. It's with a student in the civil and mechanical engineering department and another faculty. So I will briefly discuss that in the context of reinforcement learning. It's something that you might not have seen in a intro ML course. So just to show an application of that. Okay, we're not getting into the methods, but the application of that. The second one is something called choice modeling. It's a revenue management topic. So people, I don't know if anybody has taken a revenue management course. No. Okay, so revenue management is about, it's a management course. It's not really analytics course, but at the same time, analytics or data science is kind of part of many of these business courses. So choice modeling is about how to model how people choose items or things, okay, when you give them options. For example, it could be at the level of a city deciding, okay, should we have a bus option and a train option for this neighborhood? So the 2 options, And while deciding that, they want to understand if I give those options, how will people choose? Okay, and if I know that even if we keep a bus route under train station, people will only take a bus or the train, then probably you should not give both options, perhaps. Right. So that's at the policy level, but you can do that the same thing at the very in the online setting, as in the internet setting. You can say, okay, I have a 10,000 SKUs or items to sell on my Shopify store. But when people visit my store, they can only see 3 or 4 things because the screen size of the phone is very small. Then out of those 10,000 things, what are those 4 things should I show? Okay, that's the choice that I'm giving to the users. And what to show depends on how users choose, right? So that is a interesting idea in marketing, and obviously revenue management and operations management. Has implications to many things, like when you book airline routes, right? So there you will see ordering based on price, based on convenience and whatnot. But why those? Why did they decide to choose those routes? Right? So that's a firm level decision, management decision. So that's the second work. Okay, just to give a sense of the application. I'll get into the detail of them, but I'm just giving a teaser. So each one I'll give a little bit more detail so that it's more concrete. The third and fourth ones are related to vision and text, which some of you might kind of work with in your ML courses. So on the vision side, there is a problem called object detection. Okay, so which is a very popular vision problem. It's just about, okay, if you have an image, beyond classification, without, so if you have an image, then can you identify which items or which objects of interest are in the image, and then can you put squares around them or rectangles around them? It's called object detection. It's a supervised learning problem, exactly like how you do regression. You need an X and an Y. You need lots of them, and then you map, given an input, get me boxes, get me Y, right? So we, with one of the students in the department, Son, actually the previous work is also with a student in the department. But so with Son, we worked on how to adapt these popular models to an actual use case in manufacturing and transportation, where the objects are really small. And so existing models, pre-trained models are not really you can't just, even if you fine tune them, there's some limit. And so can you do something more? And so that's the third work. And last work is a very simple national application from last year. Again, how to use an LLM as a black box. So what a large language model or any of these pre-trained models do is they kind of let you not do the hard step of actually training or collecting data and actually training. Okay. So without training, what can I do for some business intelligence use case? In this case, we want to understand news data. News data is a text data. It's a bunch of articles, news headlines. They're not very structured. They don't appear in like in columnar format. So you want to kind of process them and understand, right? So those are the 4. So let's start with the first one. It's reinforcement learning. There are a bunch of faculty in the department who work in this area. Professor Selva, Professor Vijay, at least Professor Beryl. There are a lot of folks who work in this area. But we look at the application. Okay, so the application is crowd shipping, which is basically a particular type of gig work. Okay, where you have a bunch of people and you have a bunch of requests of people wanting to ship something from point A to point B. A lot of people doing it simultaneously, basically. And then you have a bunch of people who come onto a platform typically, and they'll say, okay, I can do orders 1, 2, and 3, and somebody else can do orders 3, 4, and 5. So how do you kind of do this matching of people who are willing to do the shipping and the requests that come in, and not just match, but match so that you take care of routes and like delays and things like that. Historically, I mean, it's not such a as big of a market as like a healthcare setting or something, but it is a reasonably big market. $30 billion is the estimate from a couple of years ago. And obviously there are companies, some of you might recognize, Instacart and stuff. The problem is pretty applied. It's saying is, whether you bring in reinforcement learning or bring some other analytics, all I want is an efficient way to match the people we have to ship resources from point A to point B. And there will be many such requests at any given point of time. There are a couple of aspects: time-sensitive nature. If it's food, there's a limit to how much you can delay it, and there could be guarantees also. And one of the reasons why regulation might also encourage this type of thing is because if you have delivery vehicles, then they add a lot of congestion to urban environments, which are pretty dense already. So there's all the regulation and policy angle to it. But let's say we want to do this. How do we do this? How do we do this matching? Okay, so to answer that question, you need to appreciate that this matching process is actually what is called a discrete optimization problem. In the sense you have specific people, specific requests, you need to match them. So it's an optimization problem or a decision-making problem. And you can write down something called a mathematical program for it, which is just saying, okay, here's the constraints, here's the objective. Can you match the person available to these requests? Okay, that problem is typically when you write these types of problems, not just this crowd shipping problem, but many of these what are called routing problems. They are generally very hard to solve. Okay, so I don't know how many of you have encountered the word NP, NP hardness. It just means that this problem is not very computationally feasible beyond a really small toy situation. Okay, if you want to solve it exactly, obviously you can just say, oh, I'm just going to match the first person with these two requests, second person with these two requests. You can do that. That would be just a feasible solution, but it would not be the optimal solution. To getting to the optimal solution is NP hard or very hard to do. There's obviously a technical detail here, but I'm not going to get into technical details. Okay, so the problem is NP hard, and that's why we want to bring in some heuristic technique. And in our case, we're going to do that using machine learning, or in particular reinforcement learning. So what is the operation problem? I already spelled it out to you. So it's a problem where folks arrive dynamically, and requests arrive dynamically. So two sets of objects are arriving. So dynamically just means that every 15 minutes, maybe there's like a bunch of people, new requests came in, there are old requests, new people came in to kind of do the gig work, maybe some people left. So that's what I mean. And one simple way, natural way to do this is, okay, we'll solve the problem every 15 minutes or every hour. Instead of like every time a new request comes, we figure out, okay, who to match, maybe that's too hard. Let's just solve it every 15 minutes. And there's some objectives that the companies could have, like minimizing, shipping costs and things like that. Okay, so there's money involved because you pay these gig workers some dollars for their time, and their constraints, right? The constraints are set time constraints typically. So the idea, and you won't be able to understand everything about this particular application, but the idea is to say, okay, this is a hard problem to match. We want to use machine learning. In that machine learning, there's some particular technique, reinforcement learning, which is pretty popular, and you might have seen it before, at least in terms of popular news, like how reinforcement learning techniques are able to play games like Defense of the Ancients or StarCraft, or like even Atari games, or Duke, sorry, not Duke, Doom, and so on. Okay, so there are techniques which help you make decisions by learning how to make good decisions. Okay, so that's that. So they're focused on decisions rather than forecasting quantity or giving a label. So, so as I said, the problem is hard. So many problems, many solution techniques, they solve using what are called heuristics. Heuristics just mean they're not guaranteed. They just do something clever, but they're not guaranteed to actually work in a reasonable amount of time. We have proposed a reinforcement learning technique, which with some contributions, but I'll just not really focus on the contributions that we have because that's a little bit more advanced. But the application of reinforcement learning in this area, we are not the only ones. There are some other folks in general transportation routing problems. Other folks have also, in the past 2-3 years, have applied it to various degrees. Okay? So what is the one key detail in this solution technique, right? So as I said, it's a learning problem, which means that there's some data collected, some training happening, some neural network behind the scenes that's making predictions. Okay, what is the neural network predicting? The neural network is predicting which action to take. Okay, it's very similar to a neural network predicting, okay, label 1 versus label 2. Here, the neural network is predicting which action to take. What are these actions? Remember, we want to match people to requests. So that's the overall goal, but the neural network is only going to say, is only going to take decisions which are very, which seem pretty technical, which is just saying, hey, insert a request to this person's route, or take two routes and switch the requests which are present in those routes, and so on. Okay, so it's a little bit technical behind the scenes, but these are the decisions. There are 5 points listed here. Are the decisions or the predictions that the neural network behind the scenes is making. Okay, in the reinforcement learning paradigm, the details don't matter. It's just some sort of network with some input, which is what is the current matching, what's the new number of people, and so on. And it's just making decisions at this level, which is to change the assignments. Okay, the changing assignments is, for example, insertion is like, okay, here's a new pickup and delivery. Let's insert it into an existing route. Okay, so that's an example of addition it can make. You may say, okay, if these are already the decisions, I can always try each one of them one after the other and just figure out what's the best decision to make. It's not that simple, because these are very specific decisions there could be 100 such or 1,000 such people at any given point of time, and so there could be like hundreds of routes, and so you can't be doing insertion and trying or figuring out whether it's better or not. So the problem is hard. Okay, to just enumerate, just enumerating all the solutions is not feasible at all. Okay, so what the learning part, the machine learning part, is to see some historical situations where, okay, this was the collection of people and requests, and if I had chosen one of these choices of making a match, and then I got a good reward in the sense of I could finish the delivery in time, and I use less resources and whatnot. Okay, so that's the learning part, learning from past to do well in the future. Okay, so I just highlighted action space, which is the actions or decisions that the network is making, just to give a sense of what the output is. Okay? Because it's a decision-making problem at the end of the day. Yeah, I will not get into the details of this slide, except for a picture at the bottom. This is what I was mentioning earlier, which is that there is some input, which is the situation of what is the partial, like what is the current set of people who are already partially delivering things. Okay, some information like that, which is vectorized into a bunch of numbers. And then there's some neural network, which produces like if there are 5 actions, then it produces 5 numbers of which action is the right thing to do right now. Okay, so it's some neural network. In fact, it's not even a deep neural network. It has, if people have done neural network course, then it's FC just stands for fully connected. So there are only 3 layers here. Okay, so it's a very shallow neural network, but it does the job of like picking what action to take, technical action. But the technical action boils down to matching resources to requests. Okay. Any questions here at this point?
We consider like the shortest path to get to the end goal.
Yeah.
So is it considering that part also, or is it just?
Yes. So the network here is doing all the heavy lifting of shortest paths and stuff like that. So the network, shortest path makes sense when there's a graph. So here's a bunch of agents and a bunch of requests. Okay. You get to decide, if this agent does these 2 requests, and for example, if this agent does this request and this request, then this is the route that forms. So there's no, at the beginning, there's no graph itself, right? There's a bunch of dots. You can create a bunch of like squiggly lines, basically, by collecting, which are routes on this collection of objects on the graph, on the paper, right? So it's not really a graph. Yeah. But yeah, the network is trying to figure out shortest path, because shortest path possibly lead to less costs on the for the platform. Okay, so that's it. That's for the technical detail, and that's probably the heaviest thing in this whole meeting. But here I just want to show, as I said, the problem is hard, so we can't really solve it in a principled way. So there are some simple things. These simple ideas, simpler ideas, heuristics, is what people use. In fact, if you think of how Walmart and Amazon say, pick up and we can deliver in 2-hour window in the evening or the next morning and so on. They are actually quickly solving within those 100 milliseconds or less than a second when you go to the checkout page. They're quickly solving and figuring out when to deliver. Also, it's not crowd shipping. It's a slightly different problem, but it's still the same thing where they have a sense of when they can pick up what you ordered and when they can drop off. Okay. Because you can't solve it in a principled way. You will have to rely on heuristics. So here we're just showing that how the purple curve, which is what we developed, is better in terms of, so lower is better here in terms of shipping cost. So what simulation is, there are a lot of details about what is the simulation. This is about some city scale simulation of number of requests and number of crowdsources, and we're just trying to simulate in a reasonable city how much savings you can have. Okay, so. And we've also done it for like when demands are different, like in the morning and evening times when there's more demand for parcels to be delivered compared to during work hours or something like that. Okay. So yeah, this is a work where an example of a work where neural networks exist. It's been they've been there for multiple decades. We know how to train reinforcement learning based neural networks as well as supervised learning ones. But how to kind of bridge that gap from knowing the tools, which is machine learning or reinforcement learning, to the actual application. There is a lot of steps involved, and most of the times business problems tend to may look like decision making problems and therefore optimization problems. And then you could potentially use if they look like optimization problems and they're hard, perhaps you can go to reinforcement learning, or you can use other tools also, other machine learning tools also. With the core idea being, if I know how to if I have solved some previous instances of the problem, I can learn from that to kind of just predict what should be my solution for the future instances. Okay, that's the idea. Okay. That was transportation. But let's come back to more revenue management operations problem. Okay, this is the problem of what is called choice modeling. Let me keep track of time. Okay, this is a problem of choice modeling. What is choice, right? So I want to just highlight Twitter here. So Twitter kind of shows a lot of things. X shows a lot of things like links and how many people liked, retweeted, and so on. But when you go to the homepage on the app, you get to see a bunch of tweets. There's a collection of tweets. Among the millions of tweets that are happening on that platform, they get to show you 5, right? So which 5 should they show you, right? For example, let's say there's a news event happening. Should all the 5 tweets be about the same thing, or should they be diversified, right? So it's some sort of it has a flavor of a recommendation system because there is some live tweets within the past 5 minutes, within the past hour, that are important. People are sharing and liking. There's some buzz, but what should you show here in the small set? Okay, that's the firm needs to decide, and it can obviously decide some arbitrary tweets, but then what I show will influence what the user does. Okay, so let's say if there are 3 tweets by 3 news channels, they all saying the same thing, and I just go to the news channel I like. Then what's the impact of these other news channels? They get left out. I don't know if that's a useful thing, but so there is this effect of other tweets around you, which will influence what tweet you will interact with. Just an example in an online setting. So the same thing can be done in offline setting, which is that when you go to a grocery store, if you go to an aisle, there's products placed next to each other. Okay, and those products are placed next to each other, and there's a reason why they're placed next to each other to kind of figure out, if the company, in this case the grocery store, puts the items in that way, then it's they maximize their expected sales. Actually, okay. It's the same collection of items. It's not like they're trying to hide low price items or anything like that, but they're trying to organize this. Okay? And that problem is called creating this recommendation set on assortment. Assortment just means a set. Okay, so if you have a bunch of products and you want to figure out which set to show. Okay, so you could have 1 million products, you could have 100 products. You want to figure out which set to show. So don't worry about the notation. It's just meaning you want to figure out a set. And if you show a set, which is this S here, then there's some probability of that user or person choosing an item. It's a simple. So we're just constructing the simplest models that marketing folks have built, in a couple of 2 decades ago. what is the probability of the person choosing item I? What is the probability of a person choosing item J? Okay. But the more recent work of ours, we've also looked at multiple items being chosen. Okay, so if you show 5 tweets, maybe they interact with tweet 1 and 2. Okay, that's not being captured here in this notation. And then if there's some probability with which they will like, choose, or buy that item, then you can say, okay, then what is the expected revenue I can get is the price times the probability they choose that item. Okay, so if they choose that item, I get that revenue because I sell for that price. The expected is because it's an average over, okay, there's some probability they'll choose item 1, I'll get the price 1, there's some probability they'll choose item 2, I'll get price 2, and so on. So that's the average revenue. Okay, that's why there's a letter R there. And then the problem, the decision maker's problem, the firm's problem is to maximize over the set of all assortments, which set to show. Okay, so this already assumes some sort of prediction model of how does the user pick an item given a set. Okay, so there's a prediction model involved and there's an optimization problem involved. And at scale, it is challenging. So again, coming back to the Walmart and Amazon example, if they have 100,000 products, which 5 or 10 that fit in the screen to show very quickly is a hard problem. Okay, so yeah, and they generally need to take decisions in like sub-second budgets, and so at scale is challenging. And so this work, what do we do, right? So what we do is use machine learning to do the optimization. Okay, just like in the previous case, we were using reinforcement learning to do some sort of matching. Here, the problem is very explicit. There is some explicit optimization expression that was there in the previous slide. We can still use machine learning. And in fact, it's going to be machine learning 101. We're going to use nearest neighbors to solve this optimization problem. And we know that nearest neighbors problem, we can solve it at scale, even before the evolution of all these vector databases and so on, if you've heard of them, was also pretty good in the sense we had a good understanding of how to solve them at like hundreds of thousands of data points. So what we're going to do is somehow map the current optimization, the optimization from the previous slide, to some sort of a nearest neighbor search problem. Okay, so given a query, tell me what the neighbors are, and that's going to tell me what products to show. Okay, so yeah, so that's actually the punchline of this work. And that, okay, so the nearest neighbor mapping, at least in this work, depends on that prediction problem I was talking about, the prediction model I was talking about, the probability of how a user picks an item given a set. If that parametric expression, this is like going back to linear regression, there's a parametric expression of them choosing an item I given set is some parameter for that item divided by other parameters for the items in that set. Okay, so if the set has 3 elements, then yeah.
Yeah, so are there any retailers who are sponsoring for this project? Like they want to optimize their like sales?
We try to work with some companies like Target and stuff, but this is a problem where even this, this is not even complex. Okay, this is like a very linear regression type parametric model of users. Even that is a big challenge. Okay.
So how is the data being collected for like this?
This is choice data, so we know what we show and we know what people buy.
Okay.
Right. So, and actually that type of data is also a little bit hard to get. Although we do have some data sets where we can show sitting outside the organizations, we still have access to some open source, openly available data sets to do this. But yeah, they can always see what they show and what people buy. Yeah. Any other questions here? Yeah, so that's the key idea, and that leads to a huge improvement in time. So I don't want to particularly call out any names because first of all, I did not explain any of these names. But just in terms of like lower is better. So we want to get to high numbers and low values on the y-axis. That's the goal. I mean, this is a work from a couple of years ago, so there could be more succeeding works, but just to give a flavor of what we were trying to do in this project. Okay, so somehow rely on machine learning to solve an optimization problem because it turns out they are kind of related to each other, right? ML is also about training, and training means you're solving some sort of a loss function and minimizing a loss function. So that was for using ML to solve the optimization problem. How about just directly trying to model that choice behavior? The choice behavior in the last slide was a very simplistic choice behavior. So what we can do is, okay, let's actually make the choice behavior more realistic. And this is exactly where if we show this, if we show a bunch of items and they purchased one of those items, and if I show another set of items, they purchase one or two items. If I have that data, I can also fit a much more richer model. I can use a neural network to fit such a model which maps from what did you show, what did they buy, right? So it's just input output. So you can, if you have the data, you can always build a prediction model, right? So that's what we do in this second piece of work, where I am, I'm just saying that, okay, if there are some other things you want to somehow figure out how to show the right, how to kind of show the right item. But here there's a lot of attributes, so you can build a prediction model instead of using a parametric model in the previous slide. Okay. So I want to, so the way we do it for Twitter specifically, okay, on or X data is, first of all, our items here on Twitter are not the same as the grocery items or the Amazon items. Okay. They actually change. Okay. It's the same tweet. It's not like the same tweet is kind of, the tweet from 2020 is not, it's one of billions of tweets on the platform, right? So what we do is, first of all, put into a map is easy to manage space, which is topic modeling. So you can just do some unsupervised learning to say, okay, a tweet means this is a theme or this is the topic it belongs to. So at least that's stable across time. There's some topic modeling technique there. But once you do that, then you can use, again, a neural network picture here. Don't worry about how the connections are, but left side is the input, which is some sort of history of how did the user, what did the user interact with, which themes did they interact with? Was it sports? Was it music? And then some frequency of interaction. Maybe they liked a few things, several times. And then what am I trying to show? This is the important part. What they do historically, what am I trying to show? Given that, what did they actually pick? Okay. Remember, our data set is what did I show? What did they pick? Right. If I have that, I can learn parameters and have this neural network. And once I train that neural network, I can use it for decision making. Okay. So pretty natural use of, again, a tool, ML tools that you've seen to an application here. Let me skip the slide. Yeah, so the specific data that, we actually do use the Twitter data because it was part of a academic challenge called Recommendation Systems Challenge from 2020. And so we had some number of tweets. It's not too big, but enough to illustrate the concept. So we have some numbers, but I will skip the numbers. It's basically trying to show, actually compare this choice specific model to other recommendation models that you can have. Okay, so these things are typically measured according to recall, precision, and combination of them. But all we're trying to show is that, okay, it's although we're focusing on choice, it can do better than potentially something which is just fitting input output. Okay, typical recommendation model. Any questions here? Okay. So here I just showed you, all I'm trying to say is that there was an optimization, a firm had to make decisions, and we used ML to make those decisions because we mapped it back to neural, some sort of nearest neighborhood search and nearest neighbor search. And then the second version was, okay, why restrict ourselves to parametric choice models, which is what most marketers and historically, in 1990s, 2000s, that's people used to like parametric models, and they still like it because it's very interpretable and so on. But you can always use modern machine learning and build a more richer choice model. That was the second one. Okay. Okay, so I'll not try to cover all four. I'll just stop with this one. This is the last one. This is based on vision. I'll skip the text because text you guys probably already pretty much heavily use ChatGPT and variation. So it's okay to skip the text part. This one is switching the area a little bit. It's getting a little bit away from the business decisions and so on, but still it's interesting to kind of show the gap that you need domain experts. You can't just be a pure software engineer or a pure data scientist to kind of solve many things in real world. Actually, you need domain expertise. So what we want to do is detect small objects, really small objects, and I'll show you some reasons why and how we do it. So here's an example, right? So this is what I was talking about when I said object detection. So obviously, the first picture people think of when they think of object detection is like a couple of objects and then two squares or two rectangles around the face, around the objects. Typically, you can do that with your face, for example, if you have a webcam. Like that's the type of intro tutorials you would see online. But this is an example of a more realistic situation, right? So this is a camera looking down a street, and we want to detect objects. We want to see how many vehicles there are, how many people there are, and other objects of interest. And to do that, you typically what you do is before deploying something like this, you would have to collect and annotate data. So you would get this feed, get these frames of images in that video feed, ask people to put boxes around it, and that's a pretty expensive process, but you will do that. Then once you and then it becomes again a supervised learning problem. You just go from an image to a bunch of boxes. Okay? So here's the I didn't annotate it. Okay, so here's the data where you can see that. So this I think is the annotation, not really an output of a machine learning model. Okay, here you can see that there are people here sitting around here, very small, but there are people there, and it's not been annotated by the particular labeler in this case. Okay, and yeah, actually, this is the output of our model. The annotated data is even worse. So I'll show you that in a second. So this is an example of what I'm talking about. So here, you need to do more than what a pre-trained model that has been trained on, trained by other people, is not enough. Okay, and this is a common theme that you'll see in many courses, especially in my course, in deep learning course. We do a lot of what is called fine tuning. And so this is an example of why you need fine tuning, and while doing that, why you need to be a little bit more careful. Okay, so object detection in general faces challenges when you have to detect really small objects relative to the overall image size, which is what we saw in the previous slide. And a couple of ways to fix that. Okay, and this is where domain expertise comes in. Is you can just increase the resolution of images. Okay, if you can get high resolution image, you can just go zoom into that region and then say, hey, detect the objects there. Right, that's one way. The second approach is you start with sensing high resolution images. That's like literally having high resolution cameras, or you can use image upscaling techniques. I don't know if any of you have used upscaling techniques. Like if you have used Adobe products, they also have already an upscaling tool, like a choice that you can make. And the third choice, which is what we go with here, is called tiling. Well, you have an existing image, but now instead of upscaling and doing things, you can look at an existing image and then look at parts of it, and then try to detect objects in parts. Okay, so that's called tiling. Okay, and in that approach, it still is not is not a fully solved problem, and we actually come up with a tiling approach to do this small object detection. But what are we trying to do here? Again, bridging the gap. I mean, the tool is already there. We know the problem, and there are many ways to solve it. But when we want to do fine tuning, if fine tuning is not enough, what should we do more to kind of fix this gap, the business use case, which is to detect small objects? Okay. Tiling is all about, just as I said, if you have an image, break the image into parts and let's do detection on the parts. Okay, but that introduces its own set of challenges. So, and I'll show you in the next slide. So just to recall, the objective is to achieve good detection while being model agnostic. So we're going to come up with an idea which is not specific to any model architecture. So you can change the neural network tomorrow. The same post-processing technique should work. Okay, and in general, we want to do that. So this is mostly focused on inference. So at the time where you're not thinking about training and so on, you're just talking about some post-processing so that you can do well. So the key idea is, as I said, tiling. And in tiling, we're going to create we basically want to dynamically zoom into the parts of the regions of the image and try to detect objects in it. Okay, and also figure out how to merge these detections. Okay, that's all we're trying to do. So what we're trying to do is, if you have an image, fixed image, previous methods were like, okay, let's shift the box, shift a tile basically, or a small patch, keep moving it, detect objects, and somehow merge the detected objects. But that seems wasteful. If there are large patches where there's nothing going on, then you have a forward pass, so basically some prediction step that you're doing, which is kind of useless. So we have a slight improvement on that. So this is a picture with a lot of things going on, but what I want to show is basically you start with a input. Okay, so this input has a bunch of things going on. I wanted to put a lot of travel related or transportation related objects of interest. What we do is first break that into parts. Okay, this is exactly what tiling means, like break it into parts. And in each part, you will detect something. Okay, so for example, although this airplane is going across two parts, so you'll have to detect only parts of it. You detect parts, and then you can stitch them together. While stitching them together, things which are already inside the patch, you can easily recover them because they're not crossing boundaries, so you don't have to do any complicated merging. So you already have recovered these, but you missed the aeroplane, you missed a bunch of a person, you missed a vehicle, and so on. So there are some challenges with just purely tiling and merging. Okay, so you need to do something more. And for that, what we do is focus on things which are on the boundary. Okay, so like for example, this vehicle is on a boundary, so it was detected on both sides. So anything that was detected which is close to the boundary of the patch, we can dynamically figure out, okay, let's again zoom in this region and do again a detection. Okay, that way we can find a bunch of items. Okay, and then we'll add them back into the set. So there's some extra items now, objects of interest. And finally, what happens when there's small objects and a large object like this airplane? Then for airplane, you have to figure out how to merge these boxes into a much bigger box and detect that. Okay, so that's the third part. But the whole idea is all about break the image, detect in parts, and somehow stitch the solutions together to get the full solution. Okay, and let me skip these details. Yeah, so this is the original image, and I already showed you, like a precursor of what the situation was. This is the original image, and this is the annotation. So I think the first one I showed you was not really annotation. For example, these vehicles here, they look like a huge mess, but they are actually vehicles. So they were not annotated by the labeler, right? So you can see there's a couple of motorbikes there, a bunch of people not annotated, and so on, right? So for example, here there's a bike behind this tree. They're not annotated. And there's some bike here and so on. So I'm saying is that in this business application, there was annotation issues. Here's a, if you just apply a regular object detection model, then it misses most of it, right? So it missed a bunch of people. This is a model where we didn't do anything beyond just detecting, without doing the tiling idea. So it detects most of these things, but still miss the vehicles, miss the people, and so on. Okay, and what we do, and this is a detection with ours, we are able to get the vehicles, we are able to get the people, and so on, which is an improvement over the previous technique. Okay, it may seem like a small change, but this is very important, especially if you think of security and policy, management of a city, right? And here's an example I wanted to show for a different application, which is we were trying out with the manufacturing setting. It's a towel, okay, but any clothing artifact, and there are small objects, small things that we need to detect. In this case, these are defects in those clothing artifacts, and this one is a large one, but there are small ones like those that you should be able to detect, and it's very hard to do that without doing some sort of, for example, the styling application. So first of all, you'll not be able to use pre-trained data. You probably have to annotate data and build an object detection model. Even that will not be able to detect these small things. And so you'll have to do this extra step to actually get a performance boost. Otherwise you'll not be able to do well at all. Okay, so just to summarize this one, it's a computer vision is already practical. It's actually much more lightweight than large language models and all these text models. And there are many open source models available, like companies like RoboFlow and Hugging Face. They host a lot of these vision models, but sometimes off the shelf ML is not enough. And bring this closer and closer to reality, to use cases, somebody has to kind of bridge that gap. Okay, you may not build a new architecture, but you have to kind of, whatever the architecture is there, what is the gap, domain specific, typically problem specific gaps. If you can cleverly fix them, it doesn't have to be very theoretically correct and all that, then there is a lot more potential that you will kind of unlock. Okay. Any questions about this part? Okay, I will not get into the last one because we are kind of at the end of it. Just skip this.
Would it be possible to share some material on the last example, the LLMs?
Yes. So a video of this talk is already online, but I will share this. Yeah, I think it's getting recorded, perhaps. Yeah, I can share that for sure. So we didn't see 4 applications, but we saw 3. I just want to summarize so that we have at least a couple of minutes if there are questions. Firstly, this session was about just introducing you to some research that's happening in the department, which is a little bit more accessible. We do a lot of other research. Some of it is more methodological, like new methods for solving decision problems or prediction problems, as well as estimating causal effects and so on. So there's a wide variety of research that happens in the department. But I guess this session I was just focusing on my own recent work with some students in the department as well as the university. So we saw 3 applications: crowd shipping, transportation application, where there's some decision problem, hard to solve. We use some machine learning toolkit, in this case, reinforcement learning, to solve it and show some performance improvements. And this is probably what companies like Walmart and Amazon would have to do if they want to kind of adapt something beyond the heuristics that they're currently using in their same-day delivery type of application. But crowdsourcing is what we saw. The second was choice modeling, and this is of huge interest to airlines, hotels, e-commerce, where you kind of want to understand how users choose, so that you can ideally want to put things which are pricey and give you the biggest margins, but that's not the right strategy. I mean, generally you want to maximize some overall sales or overall, sales, and maybe there are other effects like inventory that you want to manage as well. And the last problem that we saw is just using of computer vision in a specific setting. Transportation is what I showed in terms of experiments, but there's also manufacturing, where you want to detect small things, but existing tooling, even if you do fine tuning and stuff, has some limit. And so you could do either pre-processing or post-processing. We just do post-processing, which is styling and some intelligent stitching together to improve some numbers, performance numbers. So yeah, let me stop there. Any questions, comments?
About the computer vision,
Yeah.
What could be the possible application in this industry? Could it be
Those were realistic applications.
Yeah.
Yeah.
The ones that you showed about the toggle defense, right?
Yeah.
Could we possibly use it for like quality control?
Yes, that is the quality
machines?
control problem. No, this is not quality control of machines, right? This is a quality control for the products that are being manufactured.
Yeah.
So high volume products being manufactured. Clothing artifacts are the hardest because they are very deformable. If you have like just like a bottle, like let's say you're selling a soft drink, those that you can still use vision to do quality control, but it's a little bit easier problem than to work with clothes. Yeah, but the last application was about quality control. Yeah, in the manufacturing setting.
For the fourth one, the business uses of LLM.
Yeah.
So what exactly, I mean, where can we use it? And
So here I didn't get into it, but we used it.
but that one is interesting.
What we do is basically somehow convert all the unstructured news data into a graph, which is of relationships between objects of interest. In our case, news is typically about companies and their products. And so we want to kind of somehow create a graph between companies and products and get a sense of how they are influencing or influenced by each other. Okay, so this is just a very cherry-picked example of what is the relationship between Google and Apple. These are like big trillion-dollar companies, so really relationship is highly condensed and summarized in one number by just showing what happened before and after Apple introduced the privacy change. Okay, this was 3 years ago when Apple said, okay, we're gonna further lock down our iOS ecosystem, and you can't really track people as well as you're doing before. So you can see that the relationship strength in some sense, which is not really relationship sense, but in some sense, whether they're positively correlated or negatively correlated in terms of their business activities. It went from 0.71 to 0.15. These are all some normalized numbers. Obviously, I'm skipping some details, but this is some sort of an insight, right? If somebody at the CEO or executive level, they're not going to really train any network, or they're going to consume some product like this, which abstracts over some heavyweight machine learning models like an LLM, right? So here we're using a lot of news unstructured data, a lot of news headlines and article details, convert that into some sort of a graph between entities in a business setting, which is mostly going to be company names and products, and then relationships between them in terms of how they're related to each other. For example, you would get a sense of the partner ecosystem in this, let's say in the tech industry or things like that. That's the idea. This is just showing before and after these weights change, but that's a very obvious thing. But you could do something more because this is cherry picked. The network will be very huge. There'll be a lot of companies, a lot of products. So relating them is a hard task when you have unstructured data. LLMs and other NLP tools can kind of give you that abstraction, right? Abstraction. Yeah.
Okay, so how do they collect all of these data? Because if you want to do it manually,
Yeah,
it would take a lot of time and
manually
cost.
for this part.
Like for any part, like for the computer vision, you have to collect a lot of images.
Yeah.
Or for all of them.
Yeah.
So what are some like automatic like automations in data collection that they're being used?
There are automated labeling techniques, which again, they're heuristics, but so data part is pretty expensive, and that's generally the kind of the secret sauce, a big moat for many of these companies. And I think Google just signed a $60 million per year contract with Reddit, right, for getting Reddit's data. So there's one part which is like getting the data, and the second part is actually annotating it. So I would say for the third one, we actually had to get annotators. So for example, the quality control setting, we have like thousands of images, and we actually had to, we actually got some domain experts to literally sit down and put bounding boxes around the small objects. And this is the process you'll have to do. There are some platforms out there which say, okay, we can enable this whole thing, management thing of managing labelers and, curating all these annotations. But they'll also say, hey, here's a feature where we have some pre-trained models which can automatically detect automatically put bounding boxes for your images, but you still have to get verified by some domain expert. So it kind of eases your workload a little bit, but you still have to curate your data. That's for vision, but the other ones are a little bit more easier. Like choice modeling is you can literally know what you're showing. So this is mostly log data. And so these are typically tabular data. So you would know, you as a company would know what you showed and what people did on your website or app or whatnot. There's big companies on product analytics and web analytics which do that. Crowd shipping, again, it's your own. If your own form data, then it's not, I think, too difficult. But if the moment you need annotation, that's a little bit of an expensive process. Like choice model is easy because you're literally logging both the inputs and outputs. Like anytime you can log both inputs and outputs, you can just build that prediction function. That's what's going on in most of them. But for some of them, the outputs are not predetermined. So you have to figure out what the outputs are. Yeah.
I'm not sure if it works like that, but I read somewhere that when you're logging into websites and they ask you to verify if you're a human,
Yeah.
right? And then they ask you to put boxes on bikes or cars.
Yeah.
So they are actually also that's what I read, that they are actually
Yeah.
using that data to make labels.
Yeah, I mean, you have like two predominant companies in that space, right? One is your Google reCAPTCHA, and then you have HCAPTCHA by Cloudflare. So most companies, you need to have a scale effect. If you build your own puzzle solving thing, then I don't think you particularly care about how people solve the puzzle. But yeah, Google behind the scenes can use that data for the training purposes. Although I haven't seen the source of that assertion myself, but yeah, that is possible. Yeah. But labeling is a big industry. Just to say that the economy is pretty complex, and there's so many big companies out there that you might not even heard of. Even if you're in analytics and data science space, there are large companies which hire like tens of thousands of individuals, and they're ready to label your data for a fair price anytime. Okay, so you can go out and say, hey, I want 10,000 images to be labeled, and give me 500 people to work for a month. You can actually do that, right? And companies like Tesla and others who need to do full self-driving or were aiming to do that, they also need analytic data, right? So they would also hire folks either through contracting companies, vendors, and whatnot to enable that. And a big thing is with LLMs, there's actually a step where you need humans to verify whether answer one is correct or slightly different answer two is correct, and so on. So LLMs can generate multiple answers. Okay, you set what is called a temperature parameter. I don't know if you played around with that. They can generate multiple answers, and so you can ask humans to say, hey, whether answer one is correct or correct as in more preferred, or answer two is more preferred. And OpenAI, for example, is paying a lot of money to get this very curated data to tune their models, for example. And same thing with Anthropic and others. They'll do that. Yeah. Yes.
Yeah,
That's right.
so there were you mentioned there were domain experts hired for doing the boxing part.
Yeah.
So what was the scale? How many number of people were hired to do that?
Oh, in our case, or
Yeah.
ours is a tuning, is more of a fine tuning. We are starting from a well-known model. I don't know if you've heard of you only look once, YOLO model.
Okay.
But there's a well-known popular object detection model, and then we're just trying to tune it. So if you remember from your classes or something, but fine tuning, you don't want to kind of collect too much data. So we had of the order of, I'll say 10,000. So it's not too much. So in fact, there were no separate domain experts in this case. They're actually the people who manually do this quality control were asked to kind of annotate, or their supervisors were asked to annotate in this case,
So
in the factory.
In case if they miss out some details, so anyone was reviewing those things, or?
So in this prototype, we didn't do that. But here, as I said, it's not a third-party vendor. It's literally the people in the factory because they want automation, or their supervisors and their bosses want automation. So they were just annotating the data that they were collecting. Yeah. Yeah. Your question?
Yeah. So regarding requirements by the companies, they need people who can do internships in research scientists, maybe using LLMs. They have requirements of someone who knows LLMs and how to use them.
Yeah.
So if someone is willing to switch the career side, and right now we do have the ML subject, I have it in the next semester.
Yeah.
So apart from that, what else can we do or work on so that we can make that switch and at least be eligible to apply for those internship or career?
I think there's going to be a huge competitive pressure, right? First of all, these automation tools are itself chewing up and taking up some of these tasks that you would traditionally do. So there's a pressure on at least white collar workers already. Okay, because of it's just the past 3 years of evolution.
A lot of requirements, including NVIDIA. If you see, there are a lot of internships. They specifically need students who know of LLMs.
Yeah, but we do learn LLMs in our class. In my deep learning class.
Yeah.
Yeah.
Apart from that, regarding projects or something which we can do apart from the coursework.
Yeah.
So what we can.
You can just why don't you email me? I do have some resources I can send
Sure.
you. But getting expertise in like tuning LLMs, for example, I didn't show it here. In the last project, we did not, in this one, we did not tune any LLMs, but there is recently a paper that's on archive and I can send it to you as well, but it's with the same co-author, Son, who's a student in the department. We tuned, we actually fine-tuned an LLM, okay, which is a hard task. LLM, first of all, doing inference is hard on regular machines. So but on top of that, if you want to tune them, which is literally grain descent and update the weights, it's non-trivial. So, so he has, for example, he has the experience, right? So if somebody asks like, hey, have you tuned an LLM? Yeah, he can say that. But for you to kind of do that, there are a couple of resources you can try. But tuning LLMs, openly available weight LLMs, it's going to be still hard as of 2024 spring. I hope in a year or so things are going to be looking better. You can always tune like smaller, I guess the previous generation of language models, which is like GPT-2, which is there, and the weights are also available. And that one, for example, you can tune and play around with. But the more recent ones, which are more capable, it's a little bit harder to do anything beyond inference or beyond like input processing, which is RAG and prompt engineering and whatnot, or some post processing. It's a little bit hard for students to do that, I think. Yeah, but just email me. I can send you a couple of resources.
Thanks.
Yeah. Okay. I think we went over time. So thank you so much for listening. And yeah, you can put an email. And as I said, you can add me on LinkedIn and we can continue the chat.
Thanks so much for conducting the session.
Thank you.
Thank you.